One. So today we're going to do uh, the external flow in ANSYS using ANSYS Fluent. So let's open up the workbench first. In the meantime, let me describe the problem for you guys. So this is the problem we're going to do. This is the object and this is an external domain. So what we want to do is flow around an object. So initially in the first case, what we did was an internal type of problem, like we have a rectangular duct, the flow was going through the rectangular duct. So we were trying to do the flow was going inside this rectangular duct and going out. So our flow domain was inside, like restricted by the boundary of the rectangular channel. But now what happens is we want to check the flow outside the body. So what should be our geometrical domain? Okay, so our domain should be uh, it should be big enough so that nothing bounces back from the wall of the external domain back to the object. Because if you think practically, like if you take like for example a car, when it's passing when it's running, it's open, there is open space, there is no wall that the wind is bouncing back from the wall and hitting the car. Nothing like that. There is no reflection from a nearby wall. We want to do an open space analysis. So the flow is coming in and going around this object. So that's why the external domain need to be big enough so that nothing comes back or nothing reflects from the wall and comes back to the object. And if it is big enough, the reflection from the wall or maybe the influence due to the no slip from the wall would be almost zero. It would be negligible compared to the velocity. Okay, so that's why we need to make our external domain as big as possible. A standard practice, if you don't know how big it should be, make it at least 40 times larger than the dimension of your object. Okay, okay, no, so let's start. We're opening up the ANSYS Fluent. Now the geometry. I'm going to use the design modular, but you can use the space claim as well. So my object is the diameter is 0.04 meter. Um, so I would make it, if I want to make it 40 times, um, uh, so it would be like 0.8 meter, I think. Uh, and I calculate the Reynolds number, by the way. And the way to calculate the Reynolds number, I'll explain when I would be selecting the viscous model. So let's go to the geometry first. So it is a 2D type of geometrical analysis. So by the way, the practical application would be like, imagine a riser in a sea. So you want to analyze a flow around the riser. Okay, the sea wave, how it's passing the riser, the sea current, how it's passing the riser, and how much stress is it developing on the wall of the riser, or like how much pressure is like how much drag this riser is facing due to the sea current. So this kind of analysis, or maybe a cross section of a plane, you take a cross section of a wing of an airplane, we call it airfoil. So flow around an airfoil, so that you can analyze, like, with a different angle of attack, with different angle of the plane flying, how is the flow behind the airfoil, so that we can calculate the angle of attack, and it doesn't cross and the plane doesn't damage, or flight goes smoothly. So it's for design modification. Okay. So in the XY plane, we'll same drill. We'll create a sketch, and in this sketch, we will have a circle because our object is circle today. So let me okay, look at, so it's parallel just for the convenience. So I'll start with the center, so it's C. So there you go, we have P, and I'd make it small first. Okay, the dimension is in meter, so let's go to the dimension general. You can select diameter as well, but I think by default the general dimension takes diameter. There you go, D1 diameter. So my object diameter is 0.04. So 0.04. All right. So this is my object. So I need my external domain. So I will go to the circle again, the center. Now I what I'm doing is creating the external domain, a circular external domain. But you're not limited to a circular external domain. You can do a rectangular external domain. You can do any shape. You can do a triangular external domain depending on your problem. Now, my object was circular, and I created a circular external domain because it would be easier to mesh. That's the only reason. Okay, it would be easier to mesh. Another reason you can say, like, due to the circular domain, I'm skipping. If you compare it with a square one or a rectangular one, I'm skipping some space in here. So I'm reducing some of the elements in here, and the influence from here is not much. So it would reduce my total number of elements a little bit, maybe not, because I'm increasing the number of elements in here. So it's a trade-off. But anyways, it doesn't matter if it's a circular or rectangular or square domain, as long as it is big enough so that nothing reflects from the wall. That's your main concern. Okay. So let's go to the dimension. D2. D2 is uh, 40 times, so 16.16, right? If I'm not wrong. I might be wrong. 1.6. Yep. So let's start with this one, okay? And we will check the simulation result. And if you remember, in the first case, I told you guys to make a comparison with different meshes. So that is one way to validation. And if you are doing an external flow, another thing you need to compare is the domain sizes, because we are guessing this external domain, this size, this 1.6 meter external domain is good enough, but we can't be sure. So what we can do is we can take a look at the velocity contour plot and pressure contour plot and make a guess if something is hitting back. Also, it's a good practice to do two external domain sizes. So this is one size, make another one a little bit bigger, maybe 2 meter, okay, 2 meter diameter, and run the case again and see if the result around this object is changing or not. If it's not changing, then it's good enough. The external domain size is good enough. Okay. So the same way, we have the geometry. Now we are going to create the sketch. Now understand understand this. The Previously what we did was we created a surface inside the body, inside the boundary. Now we have two boundaries in here. We have an external boundary circle and a surface of the object circle. Now the flow we want to analyze is the surface in between this external outline and the object surface, right? This surface, not the internal surface of the body. Internal surface of the body has no concern in our analysis of this problem. So we want to create a surface in between these two edges or these two lines. Okay, so what we will do is the same way. Actually, it will just do it. So surface from sketches, and if you select the sketch or select one of these, click apply, generate. So you see it automatically creates so this is how the geometry module works. Whenever you have two boundaries, it will like enclosed boundaries, it will create the surface by default uh, in between the two lines. Okay, whatever the surface they can make in between two lines, it will create it. Okay, if you wanted to create the surface inside, this sketch should have only this circle, not the outer one. Okay, just in case it is clear. Now, one extra thing we are going to do in here is, so as you can see, we have one big surface in here. So this is one part. This is the surface body part. Now, we want to uh, assign an inlet and outlet. Because this is a circular body, what would be my inlet and outlet? So easier way would be if it would have been a rectangle like this, a rectangle like this. Okay, so this would be our inlet, this would be our outlet, this would be our wall, far enough. This would be our wall, far enough. But we are doing a circular domain. Okay, so the easier way would be if we imagine if we cut it like this. Okay, so this half part of the circle is my inlet, this half part of the circle is my outlet. Okay, so how we can do that? Because if you look over here, this is I hope I didn't delete it. Okay, this is a uh, s- complete surface, and if you select the edge, as you can see, this is the complete circle. How can split this one? So let me show you how you can do that. And there are multiple ways, but I will show you the most easy way. Uh, Easy way is so what I want to do is let's split instead of this line, which you can do that using a projection tool. Like you can use this projection tool and split only the lines. It will actually split the surface. Now maybe only the lines. Uh, I forgot. But easier way is just split the face, split the surface. So split the surface. That will split the edge line, the circular line as well. So what we can do is we will go to tools, face split, and now it's asking, look at in here, the option is face split by points and edges. There are other options as well by plane. So if you create a plane in the middle, you can use that plane as a reference to split this surface, or by location, or the other option. This is the easier option, the by default option, the points and edges. So my target face is, which surface do you want to split? It's asking. So I only have one surface, so I don't have anything else to select. So I'll select this one, click apply. And now tool geometry. Tool geometry means what is your reference for the splitting. Okay. So what I would do is I could have created another sketch and created a line in here. Okay. But because I started from using this axis, I could just select the axis. As you will see, I'll select the edge option, and I'll just select this coordinate axis. But if you don't have the coordinate axis, for example, I want to split it in here, so I needed to create another sketch and just create a line, straight line over here. Okay, I'll show you in a minute. So I'll click apply, generate. I think it's done. So let's see, because it's a green tick mark, so it's done. You see, the surface is split between it's two surfaces. And if you go to the edge selection, now I can select separately. So this would be my inlet, this would be my outlet. Okay, so I don't need anything else from here. Just to show you guys, I'll do this extra thing. So you go to the XY plane, create another sketch. This is sketch 2, and you could have created this line and just use this line for the face split option. This is what I meant. Like if you go to the tool, face split, and select this face, tool geometry would be, oh, I have to make sure your selection is right. Okay, so these two, and if you generate again, you'll see this surface would be split in two. I don't want to do this. Okay, let me actually show you. I'll just delete it. So if you take a look, you see this line will not play any part in your simulation because this is just a line. As long as it is not a surface or a body, it will not play any role in your simulation. Okay, because I look at always over here, so I have only one this surface body that's going to be analyzed. This line will not have any part to play. Okay, so let me delete the which one was that? Most probably split two. I'll just delete it. Sketch two. I don't need this one. So even if you leave it in here, the sketch two doesn't matter. Let me make sure everything is fine. Okay, this is what I wanted. So we're done with the geometry. So the mesh part. It's taking its time. Um, uh, okay, there you go. All right. I don't need the direction, so I'll just turn off the direction for now. So let's generate the mesh first and take a look at the default mesh. Always do that. So it doesn't look that good. As you can see, you need to, what is your critical region? Your critical region is the surface of the object or surface of the body or the cylinder wall. So we need to have a very finer mesh near here. So imagine the flow is going around the object. So the flow will not change in this region, right? It will change in here and then behind. So what we say is wake of the object. Okay, wake of the cylinder. Behind the cylinder, the flow will fluctuate depending on the Reynolds number. This, like along the whole endpoint, it might fluctuate or like start shading vortices after some certain Reynolds number, or it will stabilize depending on the Reynolds number, depending on the flow. So my critical region would be this area. Okay, so I need to have a finer mesh in this area, and I can have coarser mesh near this external domain wall because nothing is going to change over there according to, like, even if something changes over there, we don't care. We only care about the flow around this near this object. Okay, so what we can do to better mesh is go to the mesh control, the sizing, the same tool we are going to use because most of the time you are going to use this tool for all kind of analysis. Uh, so geometry, what I want to size is an edge. So I want to size this edge, and you can just press Control and select. I want to size this edge and this edge because they are symmetrical. I'm going to use the same feature. I think I have these two as well. Okay. For cylinder walls, click Apply. uh, number of division. So let me try with 30. Take a look. So, like, why did I pick the same number for this one and this one? Because the same number would be, you'll see like the lines would be from this point to this point, this point to this point, this point to this point. So it would be like a spider net. This is why I picked the same number of elements so that I can have a nice structured mesh. Okay. Uh, okay. Let's make it hard. And okay, let's generate. Just take a look at every step. Okay, still doesn't look good. Why? Because still it looks like an unstructured mesh. So what we can do is we can apply the face meshing and tell it like all cells, all elements should be quadrilateral structured. Okay, and these two faces should have all quadrilateral meshes. Let's generate, see if it is improved or not. It is a lot better, as you can see. It looks like a spider net. Now, so we can control the element size, the divisions along this direction, right? This direction. So the thickness, we can reduce the thickness around this axis, around the cylinder wall outline. But how about this line? Okay. So this is how can you control it? Always try to control your mesh as much as possible. Okay. So that you can change it anyway. So how can you control the vertical divisions? So what we can do is create another sizing. So select the line sizing, edge sizing, and select these two lines. Okay. So these two will let me control the vertical divisions. If there is anything wrong in this region, create another two lines. Go to the geometry and create another two face splits using a line over here. That would give you more control over your geometry. Um, so number of divisions, make it hard. I like to use hard because it gives me a strict control over my mesh. So I would say let's try 30. Take a look. Okay. So as you can see, this looks a lot. It became worse, right? Although it looks a lot finer and the number of elements may be a little bit higher, I don't know. But the problem was I don't have a finer mesh near the cylinder wall, which is crucial to my simulation. It's equal division. So I need to apply a bias so that it would be really fine near this wall and coarse far away from the cylinder wall. So I need to apply a bias. So it says no bias. So I need to check the direction of the line. So what I can do is apply this one. Allow. So as you can see, this line, the bottom line, goes from bottom to top, and this one goes from the object to the outer line. So it's not symmetric. Excuse me. So what we can do is let's take a look and then I'll change it. So start from fine to coarse, a factor of maybe 20. Let's see. Generate the mesh. So you'll see a chaotic mesh. It is finer in here, the divisions, and far away coarser in here, but this one is completely opposite. It is finer in here and coarser in here. Because why is it happening? Okay, it's because we select a single edge sizing for these two lines, and as you can see, they had a different direction. The line direction was different. Take a look. So the line direction was different. That's why the bias is completely opposite. So we cannot just do one edge sizing for these two lines. So what we can do is only select this one. I'm removing the bottom one. apply this bias vector, and I'm going to duplicate this one. So this would be, and the edge would be this one. And what you can do, you can just select an opposite bias from here, or easier way would be just select a reverse bias. So apply reverse bias, yes. Apply reverse bias, yes, apply. Then generate. As you can see, the direction became opposite. Okay, you don't even need to select a reverse bias from here. You can just apply the reverse bias in here and take a look at the geometry. So it became well again, and as you can see, both are finer number of divisions in here. I guess it's not very clear. So let me increase the bias factor a little bit, maybe 50, or maybe let's try 100. So use the same bias factor for both. Generate. Take a look at the mesh. It's a little bit better. You should have more finer mesh in here as well in the back region. So what I would do is I'll start with the coarse mesh, and you can later on make it finer, like how you can also increase the number of division a little bit. So maybe 50, maybe 60. Uh, this one, let's make it 60. The bottom one as well. I'm just picking up some value so that the mesh looks good, but you should check the element size as well. You can check it using these tools. I guess I haven't shown you guys. The XYZ. So what this does is, I think this is the one. Yep. So I can zoom in and you can take a look at the coordinates. So how much, what is the coordinate value in here, and what is the coordinate value in here. So you can check your element size. Okay. So this is uh, like 7.2 into 10 to the power minus 6. This is 1.03 into 10 to the power minus 3. So you can just subtract them to get the x coordinate, the y coordinate. This way you can check the element size. Okay. Like what is the smallest element of your mesh, what is the largest element of your mesh, and then do the analysis. Let me turn it off. Okay. All right, so we are pretty much done with the mesh. So what we want, the last thing to do is select the inlet and outlet. So I'll create name selection, inlet, and this one would be my outlet. As Fluent is name sensitive, it will automatically take these two boundaries as inlet boundary type and outlet boundary type. Okay. Other than that, if I want to check the drag at the object wall, or maybe pressure at the wall of the object, so you might want to do those kind of things. So what I just for the analysis purpose for the results. So what we can do is we can also create, even if you ignore these two things, this would be walls in your like solver part. So solver doesn't have an influence in here, but I want to have this cylinder wall so that I can do some, I can check some variable values at this wall. Just for these purposes, I'm doing a uh, cylinder wall over here. Okay. Okay. So this is my cylinder wall. I think we're done. So let's update the mesh because this is not updated yet. So select the mesh and this update option should come up. Update it. Wait a little bit. Yes, this is updated. So close the mesh, go to the setup, demo position. I'll go with the serial. All right, so we have in the general option. Um, so you should check the mesh if there is any negative volume or not. So it looks good. It's a pressure-based solver, steady state, a planar flow, and absolute velocity. So nothing to change over there. Uh, Energy, we are not considering temperature in here, only the flow. So go to the viscous laminar flow, and this is a single phase, so multi-phase option is turned off. Now, which viscous model do we need to pick? So let's go over the problem. So we need to calculate the Reynolds number. Now, it would be different for because this is an external flow. So for internal flow, what we did was take uh, the Reynolds number rho v. There was h over there, right? HL doesn't matter. So h was the uh, inlet area or inlet length in this case. Inlet cross-sectional area of the flow was h, and then we calculate the Reynolds number using that. But in here, uh, like what would be the h? So we are doing an external flow type of problem. For external flow, along the flow direction, whatever the length of the flow is, okay, this is called characteristic length. Okay, so whatever the characteristic length is, that would come in here, and we'll calculate the Reynolds number for the external flow. In this case, our flow is going to the positive x direction. So, and we know the diameter of the object, and because this is a circular object, even the flow is from here, the L would always be the diameter of the object. But imagine you have an object, rectangular object like this. So flow is coming along this direction. So your length would be like this L would be the horizontal distance of the object. But if your flow is going from the bottom for the same object, your L would be 0.02. Okay, the vertical height, the height of the object. Okay, I guess it's clear. Um, we are like I calculated the Reynolds number. I picked this artificial density and dynamic viscosity so that the Reynolds number is really low. The Reynolds number is 20. It is in the laminar zone. So click OK. Um, this is in the laminar zone. So the next thing is material. So we can uh, modify modify the air or the same way create one from Fluent database. I'm showing you guys this thing again is because like whoever only starts with the Fluent always makes this error. Like they create the fluid, but they don't change the fluid in the cell zone condition. So I'm showing it in this tutorial again. Like if I want to delete the air, it's not letting me delete. Anyways, let's modify this one first. So this is our fluid of this chemical formula. The density and the viscosity, we already know that. So density is 1 kilogram per meter cube. Viscosity, dynamic viscosity is 2 into 10 minus 3. is 1. This would be 2 into 10 to the power minus 3. Change or create. Yes, overwrite and close it. So if you double click, you see the properties are fine for this fluid. So we want to use this fluid for analysis, not this air. So whenever we are trying to use it, it's still in use by the surface body, by this surface body. So how we can remove this one? Go to the cell zone condition, go to the solid surface body, and as you can see, the material is still air is being used. I want to use fluid in here. So click OK, and then go back to the materials. And when you're trying to delete the air now, it's deleted. So the material is done in the cell zone condition. Check the operating condition. So it is operating at atmospheric pressure, which is in our problem as well. The only thing left is the inlet velocity, the boundary condition. So let's go to the boundary condition, go to the inlet. So as it's name sensitive, it's already a velocity inlet, but if it was otherwise, you could have changed it from here. Okay. You might need sometimes mass flow inlet or some other inlet types. Velocity magnitude, normal to boundary. Now, if I select normal to boundary, what will happen? The flow will be like this, right? Flow will like vertical to the circular um, circular line, which would all of them would have a direction to the object. But in actual scenario, the flow shouldn't be like this. Flow should be just horizontal, right? So how because of this curve inlet line, we cannot do a normal to boundary. So what we can do is we can go to the component and just select x direction velocity. Okay, that will fix the problem. So that would be 1 meter per second. Outlet, I think it's by default done. Pressure outlet type, a normal to boundary, like there is nothing. This is just atmospheric pressure. Gauge pressure is 0, so it's operating at atmospheric pressure. There is no extra pressure over there. And yeah, there is two type of pressure outlet. One is pressure outlet, and another one is pressure outflow. Outflow, you'll see. Okay, those two they have a difference. Most of the cases you'll need a pressure outlet to use. Outflow, very few cases that's useful. There's a difference. I'll talk about those things in maybe one of the maybe later on. So we're done with the boundary. Let's jump to monitor so that we can specify how much accuracy we want while we're solving the equations, the continuity, x velocity and y velocity momentum equation. Let's do 5, 10 to the power minus 5. Click OK. And by the way, if you want to monitor, let's say some reports. Okay, let's say I want to monitor the drag at the cylinder wall. How we can do that? This is why I specified the cylinder wall over there. Click new, and I think it's in here. Surface report, force report, drag force. I want to check the drag coefficient or the drag force, whichever you want. And where? Okay, where do you want to check the drag coefficient? In which wall? So I want to check it at the cylinder wall. If you didn't create the cylinder wall before, it would not have shown in here. So that's the thing. You can plot it. You can like save it in an Excel like a report file. outside, like outside, so that you can take the data, actual values. You can do a lot of things. Just play with these things. Click OK. Okay, I have this report. Print to console. I want to print it at each iteration. Okay, close it. Uh, Calculation initialization. So let's do an initialization and run calculation. Mm, so let's specify the number of iteration as 10,000. Calculate. So this is how uh, the drag coefficient should pop up. For some reason, I might have missed something. Anyways, we can always display it in the results as well. That's a better way to do it. Okay, then go to the so it is converged at 412 iteration. All the equations are converged. This is just report. So this report def is my drag coefficient value. Okay, so this is the drag coefficient value, and as you can see, it's not changing because this is a steady state problem. The flow is not changing, right? If it was unsteady, like it's depending, the flow is like maybe at Reynolds number, at a higher Reynolds number, you are analyzing a turbulent flow. The drag on the cylinder wall will change, average drag, and you will see this value will fluctuate. So this is my drag coefficient value, and they are all the same because this is a steady state, and you can calculate the drag force from this value as well using the analytical equation. Okay. There was another way to plot it. Yeah, if you wanted to plot it, I guess you needed to create uh, a report in here. Okay, maybe I'll show it later. So graphics. Let's take a look at the contour plots. Velocity at the interior surface or the surface body. Let's do all of them. As this is not a good displaying result tool, so it's displaying with the mesh as well. Let me go to the let me go to the safety post to have a better look. Okay. Close the Fluent before you open the CFD post because sometimes due to some licensing issue, it crashes if both of them you're trying to open both of them at the same time. Okay, if Fluent is open and you're trying to open the safety post, it crashes a lot of time. So it's a good practice to always close the Fluent first. It's automatically saved, so you can always go back. By the way, if you want to go back to the result of your simulation, go to the solution, not the setup. Okay. So this is our tool. So this is my symmetry surface, but you can create a plane in from here as well, as I showed in the first video. What I want to do is I want to check not at the cylinder wall, but at the symmetry one, a velocity contour plot. So I can refine it a little bit. Let's take a look. Too much refinement is not good as well. So make sure you refine it as much as enough so that you can check the layers so that the velocity uh, change or the pressure change you can actually just take a look. Like imagine if I made it 100. Even now this is good for this region, but in here it's very difficult to see like at which point the color is changing. So So too much refinement might not be good. It looks nice, but you want to analyze the flow. You want to get some useful information from your picture. So nice picture is not always a more informative picture. Make sure you remember that. Okay, I'll just go with 21. This gives me good data. So the velocity is high in here. Uh, so velocity over this region is constant. So nothing, I think nothing is bouncing back from the wall, and it is like a very like there is a due to the reflection the velocity goes over there. It looks okay. Okay, so let's take a look at the pressure. That will give us more information for this problem. So we have a high pressure in here. This is a stagnation point, so it makes sense. And there is a low pressure. Sometimes you might have negative pressure at the back of the cylinder if your flow is really high. So there is a low pressure in here. You can check the streamline as well. So what I can do is streamline domains start from, let's do inlet first. This is the number of lines, 25 lines. Let me turn this one off. So this is the streamline. It looks really bad. Let's try 50. Still it looks bad because I don't need these streamlines. I only need the streamline around the object. So what we can do is uh, create a line from here to here. So maybe, I don't know if I can do it by hand. Cut. Oops, no, it doesn't work that way. Uh, yeah, if you know the coordinates, so this is my 0, 0, 0 coordinate. Uh, uh, so, okay, let's do it that way. This is my 0, 0, 0 coordinate, and the first point would be like in here, and the second point would be here, or vice versa. So what you can do is, I know the diameter is 0.04. So if I want to create at this point, maybe 0.08. Let's start from 0.0, uh, 0.08. Let's start from 0.1. Okay, this is no, let's start. This would be negative 0.1, negative x coordinate, and the y coordinate would be maybe point negative 0.1 as well. Okay, 0.1. Z doesn't matter. This would be negative 0.1, and this would be 0.1. Okay, let's take a look at the line. So this the line is in here, so it looks good. Lucky me. So I'll modify the streamline. So you can double click the streamline. Instead of inlet, I'll select the line 1, click apply, and as you can see, it's giving me a better information, right? I can increase the number of lines. Not good enough. Maybe 400 lines. Velocity forward and backward. Oh no. Reduction factor. Anyways, maybe increasing it a little bit more. I don't know. Anyways, play with it. You should see the vortices, stable vortices forming at the wake of the cylinder, as I have shown you guys. Like if you just search in YouTube, like how the flow around this kind of cylinder would be, you can take a look, and for the laminar flow, you should see some stable vortices forming over here. And for turbulent flow, it starts trading the vortices. Okay, so do use this kind of tool to for displaying the streamline. The drag coefficient value, I showed you how you can get the value from there, but there are other ways to get it from there as well. You can even plot, and you can even do an XY plot. Let me see. You can even do an XY plot, and x-axis you can say my velocity, or maybe the data series location is streamline one. I guess you cylinder wall, you have to create it again in here. Okay, so you can create the cylinder wall, and along the cylinder wall you can just check the drag coefficient value. Anyways, let me know if you have any questions or concerns. We'll do more in the following.